Let's talk about sharding today, but a very special kind of it called geosharding. So what do you do in sharding? You take a database and along with its index and split it among multiple nodes. Then you have some mechanism to find out which node contains the key that you're looking for or the data you're looking for, and you go to that node and you query that node and you get the details for that key. In geosharding, the index that we want to separate our data on or split our data on is geographical, which means that if there are 4 shards, the items on shard 1 would be geographically closer to each other than the items of shard 2 and shard 3, ideally. Similarly, the items of shard 2 would be closer to each other than the items of shard 3 or shard 4. You can also imagine like a map, and each shard would represent a particular area on that map. Well, why do we need this kind of sharding? Well, there could be many applications. Let's say the app is storing restaurants and the reviews, and the user wants to see the restaurants near him. The app can just look up the shard covering the user's radius or representing the user's radius's area and just query that node or just query that couple of nodes. This would minimize the number of nodes the query needs to touch and combine the data. This would increase the performance of the query. So since the data is also distributed geographically, it makes sense to shard it geographically as well. But how will we achieve this? Let's take a look at a real life case study from Tinder. It's not easy to find you your next love. It takes a great deal of clever engineering. They wrote 2 blog posts on how they geosharded their users on an Elasticsearch clusters. And we will talk about it. We will not go into specific details about how they did things on Elasticsearch, but the fundamental ideas behind geosharding. First of all, geosharding makes perfect sense for Tinder since it is showing you people from a particular geographical zone. So, like our previous example, they would know the minimal number of shards they need to query to get singles around you. But before we understand how they did it all, we need to understand how can you encode a location of a user in a database. Ideally, we want to represent 2 locations which are closer to each other with 2 binary values which are closer to each other as well. And when binary values are closer to each other, it means they share a longer prefix than values which are further apart. First, let's not think about the location encoding and all these things. Let's start with a very straightforward and naive way to achieve this. Let's say we want to show the users the restaurants in a particular radius. Well, we could store the latitude and longitude positions of each restaurant, and when the user requests, we draw a circle around him and then go through all the restaurants and see which restaurants lie within that particular circle. Now, this would give us a perfect answer. But, well, this would be pretty slow because we have to go through all the restaurants and then calculate. Well, we don't want to do all that. Let's try something next. Let's divide our map into many cells like a grid, and our user is in a particular cell in that grid. And you see the restaurants are scattered across cells on that whole grid. Now, we still have the exact location of each restaurant, but we will also store the list of restaurants in each cell of this grid. Now, when the user requests, we will take some cells around the user and return the restaurants that are there on those cells. This will certainly be less accurate than drawing a perfect circle, but this would be much faster since it's easier to iterate over all these cells and just give the results back. But how do we create these cells on a map? How do we determine which cells to check for a given request? This is the problem that we're ultimately trying to solve, and when we solve this problem, we will see how to encode each location. Now, here's the fundamental idea. The operations that we want to do on this 2D plane or a 2D map, it would be much easier if we could do it on a 1D line or a line segment and then translate it to the 2D maps somehow. Straight lines are much more easier to handle than 2D lines. We can represent each point on a straight line as a single value and not some pair of coordinates. So it seems that it can help us, and there would be many other algorithms like segment trees and all these things which can operate on a 1D line or a line segment and give us very fast results to query on data like this. But we'll have to find some way to represent that 2D map as a 1D line and convert coordinates between them. There is this mathematical idea called space filling curves, and they are meant to map a 1D space or a line to a higher dimensionality space like a 2D map. For our use case, there is a very good space filling curve called Hilbert curves. which we will try to understand. So let's say we have a 2D area with points scattered all around. We will divide this area into 4 parts. This is the cell structure we want at the end, and we will work backwards from this to see how the Hilbert curve will give us these cell structure. Then let's take a line segment and bend it and draw it on a 2D surface, a continuous line. You will see this bent line can be divided into 4 line segments. These 4 line segments will give us our 4 cells. We will call them 0, 0, 0, 1, 1, 0, 1, 1. So as we are going along the Hilbert curve, as we are going along the line segment, we are increasing our binary number representation. Now we will just consider the points which lie closer to each line segment to just lie on that line segment, and we will give it the same binary representation. So all the locations in a particular cell will have the same location encoding. This is an approximation that we are using to make things simple and efficient, to represent a location not by its particular location but by its cell ID. Now you would see our location representation is pretty inaccurate right now. I mean, this point and this point would be encoded the same, but they're not very close to each other. How to make it more accurate? Well, we have to make our lines more convoluted and have smaller and more detailed cells. So in the end, we want to represent our cells like this. We want to have smaller and more detailed cells. So let's try to represent it with a Hilbert curve. Here's the fun part with Hilbert curves. We can recursively extend it and make it more detailed like a fractal. So what we saw earlier would be level 1 of the Hilbert curve, and we can go deeper into more levels. To fill this space, let's repeat ourselves in these 4 parts and draw the curve we drew before. Now we see that that curve was representing a part of the map with 4 cells. So we will repeat this curve and represent the 4 cells in each part. Now we want to connect these 4 curves and make it a continuous line, because we want to at the end represent the 2D map as a 1D line. Now you will see at this state we cannot just join these lines and make it a continuous line. So what we would do is rotate the bottom 2 curves and then connect everything to form a continuous line. So we can follow the same rule to make the Hilbert curve more detailed and our location more accurate. We would repeat the Hilbert curve from the previous level in the 4 parts, and then we would rotate the bottom 2 and connect the Hilbert curve. So we would get one single straight line, a very convoluted straight line, to fill the whole 2D map. Great, now you see how we can recursively make the curve more detailed and a location more accurate. But how will we assign cells the binary numbers that we did earlier? Well, at the first level, it's 0, 0, 0, 1, 1, 0, 1, 1. We gave it numbers along the Hilbert curve. We will do the similar thing for the next level as well. So on the first level, we gave 0, 0, 0, 1, 1, 0, and 1, 1. So inside that larger area, each cell would get 0, 0, 0, 1, 1, 0, 1, 1 along the Hilbert curve as well. So we would get now a 4-bit representation for a particular cell. So as we go deeper, the number of bits required to represent a particular cell would be larger. Now, since everything is on a straight line, we can find out people within a certain radius pretty efficiently. And let's say you want to find the people around this point. We can just take the cells which lie around this particular point on this line segment of the Hilbert curve. The major value that this encoding gives us is if the binary numbers or the binary encodings or the cell IDs are closer to each other, then there is a higher probability that they are closer geographically as well. Now we know how to encode a 2D point to a binary number. The method that Tinder uses is pretty close to what we discussed, and they use something called Google S2, which uses a S2 curve, which is based upon the Hilbert curve, but they account for the Earth's spherical nature. Whatever work we did till now was based on a 2D map, which is a flat surface. But the S2 curve accounts for the spherical nature of the Earth. They do some nonlinear transformations on the data and give you a more accurate encoding. We'll not go into deep of what an S2 curve is. You can read it from the description. I will not go into the depths of what an S2 curve is, but you can see it from the link that I will give in the description. So with this location encoding as an index, they can distribute the locations on multiple shards. But how to plan it? Let's call the encoding of the cell that we did the cell ID for the purposes of this video. Each user will get their cell ID according to the cell they are currently in. Now we will have to distribute these cells along with that their users to multiple shards. The first thing that we need to think about is that not all cells are created equal. For example, the cells which lie on Bangalore or on New York will have much more users than the cells which are lying in the middle of the Amazon rainforest. So if you just say that cell ID from 1 to 10 would be part of shard 1 and cell ID from 11 to 20 would be part of shard 2 and so on, there would be much more pressure on some cells and much less pressure on the other. So it would be very unequal. To solve this, Tinder created a load score for each cell. This is their guiding metric. Now, they did not give the exact formula for the load score, but it can be based on things like the number of users, number of queries in 1 hour, etc. Now, if a shard has multiple cells, the load score of the shard would be the addition of the load scores of all the cells that it contains. Now they find out the standard deviation of the load score of all the shards, and the lesser the standard deviation, the more equal is the load on all the shards. Look at the pseudocode that Tinder gave in their blog. They want to find out the best sharding configuration for them. First, they calculate the total load score of all the cells, and then they have a range of 40 to 100 cells, and then they find out a range of max load they want to have per shard. They are calling this max load they want to have per shard a container size. Now they are adding the load score of each cell and assigning it to a shard and stopping till they are just under the maximum load score or just under the maximum container size. Like this, they calculate the load score for each shard and then they find out the standard deviation. The configuration with the minimum standard deviation is the ideal configuration. Now keep this in mind, this is not necessarily the number of physical shards or physical machines that they will have, but this is the logical shard grouping. You see, because they defined the correct metrics at the beginning, which of the load scores and the standard deviation, optimizing things is easier for them. So always define correct metrics that will matter for you. Let's try this all together and see what happens. When you want to see singles around you, you would send a request from your device, which will carry your latitude and longitude location. The Google S2 library would convert the latitude and longitude to a cell ID. Now you have the mapping of which cells are held in which shards. So we'll go to that shard and query that. There is one last thing that I want to discuss because I found that interesting, on how to distribute the logical shards into physical shards. It is important to understand one thing. Remember the pseudocode I showed you earlier, the locations are being assigned to the shards consecutively. That means they're closer to each other. So as I mentioned at the beginning of the video, each shard would represent a particular area on the map, a particular continuous area on the map. Now let's say one logical shard represents Bangalore and the other logical shards represent New York. They will not have the load on the same point in time because they're in different time zones. Now let's say all the logical shards from North America are in one physical shard and all the logical shards from India are in other physical shards. Now let's say all the logical shards from North America are in one physical shard and all the logical shards from India are in the other physical shard. At a particular point of time, one physical shard would have peak load and the other would be idle, and another point of time when the time zones flip, the other physical shard would have peak load and the another would sit idle. They need to make sure that each physical shard has a good mix of logical shards from across time zones so that the load on each physical shard is more or less equal all the time. So how did they solve this problem? Well, one option is to manually go over all the logical shards and put it into the physical shards so that they have good distribution. But this is complex, this is time taking, they would need to recalculate the whole problem every time they want to reshard. So we can't do that. They boiled this down to a probability problem. So they have this number n, which is the number of physical shards multiplied by the number of replicas of each shard, as each shard would have multiple replicas as well. So that would be the total number of hosts, physical hosts that they have. And they take a particular point in time and group the logical shards into m groups according to the requests per second they receive on that particular point of time. So logical shards from RPS A to B or request per second A to B would go into group 1, and then B plus 1 to C would go into group 2 and so on. Now if they randomly distribute the logical shards on the physical hosts, they would need to calculate the probability of at least 2 logical shards of the same group getting into the same physical shard. They need to reduce this probability. So they played with the number n adjusted the number of replicas and the number of physical hosts to find a sweet spot and know how many physical shards and replicas they need. So this probability game helped them to find out the number of physical machines they need so that on a random distribution, the load is more or less equal on the nodes. Now, they would also consider other factors like cost and availability and all these things, but they would ultimately get to a sweet spot. All right, this is all I had for today. This might have been a longish video, but I guess we learned a lot. Make sure to read the whole blog post that I have linked in the descriptions. I will see you in the next one. Leave a like on this video and subscribe for more content like this.